Hello, camera. Thank you. It's 2:30. That means it's either... Actually, it's not going to work if I say it like that, is it? Let's start again. It's 2:30. That means it's either time to stream or time to go to the dentist. Tish. Right. Got that out of the way. Okay, what am I doing today? Well, I have a number of projects where I receive logic analyzer traces of data dumps from displays, and I have to take those traces and decode them and create emulator systems to interpret the data, re-render it out and output it to a different display. Basically, it's for things like keyboards and samplers and that sort of thing, where they've got a built-in LCD screen, and the LCD screen breaks because they're old, and you can't get them anymore, that type of LCD screen, because they are custom made for that specific device. So one of my friends creates replacement screens for them. And what he does is he rips them all apart, he analyzes them all, works out how they all work. Then he connects up his logic analyzer to the display, captures all the data, and then sends me that data. So it's then up to me to work out how the display works, how the protocol for the display works, because most of the time they're not documented. Reverse engineer that protocol and create an adapter that'll read in that protocol and render it out as a standard protocol for a standard LCD screen. As part of that, it would be nice if I could take his traces and output them as if I had the actual sampler or whatever in front of me, so that I can test my code and designs on almost live data. So basically being able to replay his data dumps. That would be really nice. So I'm going to see if I can design, just using a simple microcontroller, a USB connected interface that will allow me to do that, basically. It should be simple enough. I need to turn my lights on, don't I? That's a bit better. Oh, well, no, you can see me now if that's not good. Yeah, basically the logic traces he sends me are up to 16 channels. And that's pretty simple and straightforward to output as a single port on a PIC32, for example, which are all 16-bit ports. But I have choices of how I actually want to implement it. I could have it so I just take the raw dump, feed it out through USB, and then just output the data directly out through the pins. That's the simple way. But it's not ideal because I would like to have it bidirectional. So what I'm thinking is a slightly more complicated system whereby I can read and write over the USB. Anything I write gets written out as if it was a microprocessor bus. Anything I read performs a microprocessor bus read, captures the data, and then returns it to me. Of course, there's no standard microprocessor bus, so I would need to have some way of changing the personality. So it could be an 8080 bus, it could be a Z80 bus, it could be a 6800 bus, something along those lines, a 6502 bus. The idea, though, is that it'll only be 8-bit, an 8-bit bus, with possibly a few address pins so that I've got a range of addresses that I could read or write from. That's the way I'm thinking of doing it. So I've got a PIC32 board here. This is one of my own design ones. This is the ChipKit MZ Lite board. It's based around the Fubarino MZ, so Fubarino SD rather. But this has got an MZ chip on it rather than the MX chip. This one's a bit crusty and grotty with flux and what have you from years of abuse. Let's get a better view of it on the old mobile here. There we go. Can I zoom in on here? I can. It goes a bit grainy when I do. So yeah, that's the MZ Lite board. It's a PIC32 MZ 0512, yeah, whatever it is. 200 megahertz, half a mega flash, 128k I think it is of memory on it, RAM on it. It's the cut down version. I have got a different one, the MZ Pro, or Pro MZ rather, which has a much more capable chip on it. It's got 2 mega flash and half a mega RAM, but I really don't need that for this. But what it does have is USB 2, 480 megabits per second, which should allow me pretty good USB communication. It's got a whole port available as one single block of connectors on here, as port B, which are on all the analog pins down the side here. 16 pins worth that, which is convenient. So I may well be using that for the actual I/O. So yeah, I mean, 99% of this project really is software development. So you're not really going to see me doing very much with the hardware here, just mostly working in software. So it'll be a two-part thing, writing the firmware for this chip and writing some software to interact with it. Because I would like, and most of these boards you would normally use serial basically to communicate with, which I mean that's fine, but it's a bit awkward at times. Because you've got to, if you're sending more than just one byte, you've got to work on sort of packaging it and creating a protocol, and you tend to have overheads and inefficiencies with it where you're ending up sending data as ASCII and it's using twice as much bandwidth as you really need. I'd like to keep this as light and efficient as possible. So I'm probably going to create a HID, human interface device interface to it. But that of course will mean requiring special software to do the communication. But that's fine. I work on Linux, so writing that sort of software is no problem. Not like I was on Windows. Ugh. So yeah, a bit of Linux programming, a bit of firmware programming, and hopefully a bit of testing. I don't know how much I'll get done today. I'm not going to spend too long on stream today. Only sort of probably an hour and a half, probably finishing about 4 o'clock today, I think. So yeah, I suppose, yeah, let's crack on with it. I think I know roughly how I want this to go, so over to my computer. Right, I'm going to start off, make this a bit bigger so that you can see what I'm typing. Let's start with, call it plus emute. Okay, and we want firmware. I really wish I could type. It would make my life so much easier. Oh, ISO? No, I'm working with CD-ROM. INO. Okay, so let's just start off with the basic empty sketch. Now, I need one of my Magic Make files for this. That one should do the job. Stuff in here I don't need. Right, at this point, what chip board is it I need? Arduino CLI board list all the boards I've got installed. MZ. Oh, try grabbing. Okay, the MZ light is that there. My Magic Make file. USB equals Z custom this. Anything for PyOSM. Now all this is different now, isn't it? I shall come back to those bits later. Should be opt. The install stuff is all wrong. What happens if I do that? I think we need to install. Okay. Ah, of course, got no bin, have I? What's happening here? Why is it saying nothing? What am I doing? Engage brain. Been a long week and it's only Wednesday. Right, invalid option. I don't know what the options are. So, Arduino 15, packages, chip kit, hardware pick 32, blah, 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 boards. And it's a capital USB, isn't it? USB Z custom. So opt here is USB is Z custom. Right, okay, that compiles now. I've got a right, so bus emu INO hex is what it creates. Sketch is should be INO. Okay, bus emu INO hex is up to date. Right, basic framework done. Now then, I need to start off by defining my own USB device. I'm using a custom device setup, so I can't just use off-the-shelf stuff. So I need, I remember it's been a long time since I did this. First off, create the USB high-speed device. And I want, that's all I need, I think. Then I need USB manager. the USB device there. So the USB device is attached to the manager. Then I give it a vid and a PID. F055, free open source software. And a number, what do I want? I'm going to use 8088, I think. Give it a name for the company. And a device name. Okay. I think I shall put that as capitals. And does it compile? It does. Now then, I need a raw HID device, and I cannot remember what this is called. I wrote this USB stack. I can't remember what these devices are called. So let's have another look in here. Okay, pause, pick 32. We've got all sorts of devices here under USB. We've got audio MIDI, CDC SCM, file system, HID joystick, HID keyboard, HID media, HID mouse, HID raw, that's what I want, HID tablet, USB HS, everything you could imagine. Okay, so HID raw, but if I just look in USB.h, that's got everything that you need. But if I now look for raw, no. HID raw, there we go. So I need to make a HID raw device, and onto that I can attach on output report. So HID raw on output report. I shall copy that. So the HID raw HID, and here USB.add device HID. Then HID dot on output report. Output report received. Right, this is data and units 32T len, if I remember rightly. Output report received. That should compile. Yes. Okay, let's have a first test of this. I shall plug in the board to my USB. Enter bootloader mode. There it is, hit bootloader. And now then, uploading is do this in the make file actually. Install is Arduino CLI upload -b board. Now there's a, is it input dir? I'm not sure. Seems to like it. Enter programming mode again. There it goes. Bam. And what do we get? Hey, we get new high-speed device, the bus emulator from Magenco Technologies. We have the basic device there. Excellent. That's how easy this USB stack is to make your own stuff with. I made it so that it was this easy because I like things to be easy. It was a lot of work building it originally, but worth it, I think. So, yes. Hey, Marinio, hey. Nice to see somebody chatting at last. Off to the post office, okay. I'll be here for another hour or so yet, so run. Right, so. Where was I before I was distracted? Yes, we've got the working USB interface there now. So what we want to do now is do something in the output report. Have I actually programmed this so that I can read and write? I can't remember. We can do setup in and out. That's on enumerated, get and set features. That's for feature requests. Output reports is sending data from the computer to the device. I can't remember quite how I've got this set up. The main bulk happens in these. On in packet, return false, right. So we don't do in packets, only out packets. But we have send report, that's a point, yes. And we have feature requests, which acts a bit like memory. A HID report is 64 bytes maximum. So we can send reports or receive reports of up to 64 bytes. We receive a setup packet. Its feature request port is here, so it returns one of 255 to 256 feature values. And here on out packet, if it's a feature request, then store the data into the feature. So we basically got read write shared memory of 256 bytes. that we can share between them, which I could use for the configuration side of things. Things like setting the speed at which it operates, the bus style, whether it's 8088 or 6800 or Z80 or whatever, that could be done through the features. So a write will just be a sending of a packet, which is the output report handler, which I've just created. So whenever a packet is received, that'll be received into there. But doing a read, it's going to be a two-stage thing, isn't it? I'm going to have to send first a request to do a read. At which point a read will then be actioned and then send a report back as a separate operation, won't it? Yeah. I think that's how it'll have to happen. So I need something in the report structure to say this is a read rather than a write. So what I'm thinking might be, if I were to have a 2-byte report, keep it very simple, a 2-byte report where you have the first byte is the operation and the second byte actually no, it doesn't even need to be a 2-byte report, a 1 or 2-byte report, where the first byte is the operation and the highest bit of the first byte is a read-write flag. The following 7 bits, or a subset of them, can be the address that you're doing the operation on. And then if it's a write operation, a second byte which contains the byte to write. I think that might be how I'll have it. So output report format. So we have bit 7 as 0 for write, 1 for read. Then I'm not going to have many address pins, probably only 4, so not applicable for these. And that shall be address 3, address 2, address 1, and address 0. Byte 2 if byte 1 7 is what 0. Byte to write. Okay, so although actually, do I need? I don't know if I need the top bit there, do I? Thinking about it, because if it's a read operation, it's a 1-byte packet. the write operation is a 2-byte packet. So I don't need that because I can just look at the length of the packet to know what kind of request it is. One or 2 bytes. If 1 byte read operation is started at address specified in first byte. If 2 bytes write operation is started using data in second byte to address in first byte. That's simple enough. If len equals 1, else if len is 2, write data not data 1. And that's basically the logic. I just need to write these functions now. Okay. So I will need a function for doing a read and a function for doing a write. Let's clean this up a bit. Okay, so now I need to think what features there are. Feature 1 I shall have as bus format. 8088. Z80. 6502. Some of these may be the same. 6800. Okay, 2. Now I can have all sorts of delays on this, can't I? If you think about a typical waveform, you have certain sort of delays between addresses being set, write going low, and it sets the data pins, all that sort of thing. So if we think yeah, this is going to take a bit more thought now, what features are going to be available. Let's just see if I can get my whiteboard out. Not very white now. That's our desk view. Fuzzy. Let's get some pens. Come on, focus. Thank you. Okay. So typically a waveform, you have, let's take a write cycle first. So we've got the write signal, which starts off normally high. You've got the A0 to 3 And you've got the 0 to 7. Okay, so what you normally have is the address would be set first. So the address has its value changed. Then the data would normally be changed. Okay, so the data would change its value. Then the write would go low for a period, then go high, and then the address and data are free to do their own thing again. So we have points of interest at... Oh, you really can't see that green, can you? Let's try... let's try red. So we have points of... No, even that. They're not very good pens, these, are they? Right. Brown. That's a bit better. We have point of interest here where the address changes, here where the data changes, here where write goes low, where write goes high, and where the bus is released. So we have various delays we can look at. We've got the data setup delay, the write delay, the write length, and the post delay. Sometimes there's a slight difference in that instead of a simple write, you have an RDWR signal, which may go high for a write or low, I don't know, it could vary from bus to bus. But then you have you could have a... I don't think what the signals are often called. I mean, I'll just call it E on this. So it's on LCD screens, it's often called E, where you would have an extra signal. So you've got one signal which says whether it's a read or a write, and then one signal that says do the operation, as opposed to one signal that says do a write. You might have individual memory and I/O reads and writes. You may have a combined read-write for memory, a combined read-write for I/O. You may have a combined memory/I/O selector and a combined read-write. We may have a combined memory and I/O, or separate reads and writes. There's so many permutations you could have. So on this one, there's an extra bit of interest for here. So what numbers do we want? Well, we want data setup. I think we want data setup. We want write delay. We want I'll call this clock delay, clock len, and write len, and then release delay. So we've got data setup, write delay, clock length, then write length, which gives us that can be calculated from that length being that length, subtract those, it gives you that, and release delay. That's for a write. For a read, it's a similar story, whereby you have the a 3 to 0, say the address gets set of where you want to read from, then the read signal is activated, and then at a certain point here the data on the bus changes to be valid data, and then the read signal rises and the buses are then released. So now we have the start time there, and we've got then straight into the read delay, followed by a wait there for the bus data to become stable, followed by a delay there until the read signal rises, and then a post delay there. That one can be the release delay. The read delay could be the write delay, which could then also still have these four are all incorporated into here, isn't it? Yeah, I think. So I think I can get away with just those 6. Maybe adding a few later as I think of them. So we shall have the data setup. That'll either be the delay between the address and the data being set, or the delay between... Actually, do I even need that? As long as the length of the read pulse is long enough, I don't really care about that. Do I? When I'm performing a read, that delay there is imposed by the bus, so I just need to make sure that that's long enough. So yeah, I don't actually need to know this length here. I just need to have a full length for that, with the option of the inner clock signal. And I don't even really need to care about the release delay on the read, but I do need it on the write. So I think that's enough. I need a six values, but not all be used for read. So I shall have data setup. And write delay is how long after the data is all finished setting up. On a write, the data setup would be where the data is settled. On a read, the setup delay would be from the address. That's where it's settled there. So I would have data setup time, then it's a settle time, then we have, and that's settle time is the write delay or read delay, actually this time here. Then we have clock delay, clock len, and write read length, so operation length. Clock delay, clock length, and operation length. And release delay. Those are going to be all my features, I think. Oh no, I need one more. Actually, I might go. Let's move these up one more. No, actually, I don't need that. I was thinking I need a bus speed parameter, but I don't. That's defined by all these. Now, these are 0 to 255, so what would good units be for this? Microseconds? Up to 255 microseconds? What would be the slowest we could have then? If I have the operation length as either, if it has the internal clock, the sum of delay length and overall length, or should I have the length as that is always being shorter than that? Worst case, I have that as shorter, so I have 1, 2, 3, 4. So we're talking 4 256s is, we're talking about 1 kilohertz maximum frequency. So one kilohertz, yeah, minimum bus frequency I'd be running at then if that was microseconds, which I think is perfectly good. Yeah. So those can all be microseconds. Right. Everything is going to be triggered from in here, so I'm not going to need anything in loop, as far as I know. Oh, that's camera is annoyingly twitchy, isn't it? Oi, stop it. Can't focus, can it? Go into here. Focus, focus, focus. Turn off that. There we go. Manual focus. As good as I can get. I'll leave it stuck on that forever now. I do have a little bit of zoom actually. Oh, there we go. Bit of zoom. Right. So I think I have a plan for this now. So now it's a case of implementing all these reads and writes for the different bus formats. Okay. Right, let's go back to here. Right, so you can see what I've been writing in the background now. My list of features, which are the parameters that we'll be working with. Right, let's have a look at the 8088 bus waveform. Output bus cycle of 8088. Okay, so this one, camera out the way that, we have a clock signal. We have, because it's a multiplexed bus, it's slightly more complicated. We have the address out up to there, then we have the data out there, and then the write goes low, and then it occurs on the clock, doesn't it? This is all clocked, this one, so that would be the clock delay and clock length, I suppose, wouldn't it? We have 4 clocks. One is set address. Two is set up data. 3 is perform write. 4 is release bus. I mean, I'm not wanting to implement the entirety of this bus. It's only really the end result of the bus that you see, because the 8088 bus is never really seen, because it goes immediately into address latching and decoding. So what you see normally is the decoded and latched address from the multiplex. You'd never actually see the multiplex. So this section here where it's latching the address through the data pins, I'm never going to actually create. I'm just going to set up the address, next clock cycle, set up the data, next clock cycle, do nothing really while it does the write. Next clock cycle, release all the bus. So I need to nominate pins. I'm using port B 0 to 16, so 0 to 7, D 0 to 7. 8 will be I'm not going to be differentiating between I/O and memory. I will have, or will I? No, I won't bother with like a decoded chip select line, because I could theoretically just use any of the address lines and chip select lines in my operation. So I'll take it as if the address lines are already decoded into a subset of address lines within a chip select. So 8 I shall have as clock, 9 I shall have as write, 10 I shall have as read. I don't need to worry about ALE or IOM. Actually, we'll just have those 10, I think. Okay, so write 8088. Address data. I'll have pin D0. D0 to D7 will always be 0 to 7. And what is pin number on here? Desperately need to replace this. I must go live with the new version of the website. Okay, products. Z light. Okay, so A0 to A15. Pin 15. Anyway, A0 is B0, if I remember rightly, which is B44. Although if I'm doing it pin by pin like this, then it really doesn't matter. Yeah, stuff it. So we'll go 44 for D0. 43, etc. 3, come on, 3. 41. D4, 40, 9, D5. 38. Probably not going to use these. 37. I'll just use a loop. Pin 8080. CLK would be 36. And right 35. Read 34. Okay, so good point. Address pins. I'm going to have 4 of those, I think. I'm going to put them as 8, 9, 10, 11. And move these. Four, 3 is 33, 32, 31, and 30. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Leaves me 1 spare pin. That's not many spare pins. Actually, I might drop it down to 3, actually. 3 address pins. So 30, 32, 31. Okay. So for this, I need everything to be output. So 31, I less than 44. Okay, all of them are output. Set the clock to default high. Okay, so we're here at the moment. So we drop the clock, set the address, raise the clock. Drop the clock, set the data, raise the clock. Drop the clock, raise the clock. Drop the clock, raise the clock, release. Done. So I want to do feature data setup to feature data acceptable 3 feature clock delay 4 feature clock len 5 feature clock len 6 feature release 7. Okay. So we start off with good point. How do we get the features? Just get feature and set feature. That's useful. Feature clock delay. Is that right? No. Starting off high. Theoretically, it should still be high from the last time anyway. So what we want to do is we go low. We have a delay, but in here we set the address. So we digital write pin A0 address and it's 01, 1, 0, high, low. Do that 3 times for the 3 bits, 1, 2, and 4. Okay, so we've gone low, we've set the address, we've delayed clock bell. Well, this is a symmetric clock, isn't it? So we really need the 1 value for this. We then go digital right, pin 8088, C, okay, high, clock goes high. Come back. And we have another delay. That's the end of the first cycle. We then go low again, the second cycle. Block 2, set the data. So now it's digital right, pin D0. I shall do this in discrete values. Could do it in a loop, but it's not enough really to worry about. It won't make it any more efficient. The loop would probably unroll for this little bit anyway. Okay, so we've set the data. We now have our delay. Raise the clock and another delay. So we've lowered, set the data, delay, raise the clock, delay, end of cycle 2. On to cycle 3. That's just a simple formula to the right. Is low, delay, high delay. Release everything on clock 4. So this is once it goes high, it releases. So we shall go pin D7, I is less than pin D0, because the numbers for the pins are backwards. So D7 is the lowest number, so start from D7, go to D0. Pin mode I input. Do I want to pull up? I should do really, yes. Bus would normally be pulled up, wouldn't it? But I'll leave all the other pins as outputs because they would normally still be outputs. Okay, so that should be a single 8088 write cycle implemented. Possibly. I wonder if there's an input on this same URL. That would be nice. Hey, there it is. That's useful. change the word output to input on the URL, and there we go. Right, so an input one is very similar. We have clock lowers, address is set, rise. Okay. Second one is setting the second part of the address. It takes 2 clock cycles to do the address. First one is from the multiplex. Second one is from the rest of it. So 2 cycles of address, clock lowers, delay, clock rises, and it will do the read at that point in T3. Clock lowers, data is released, clock rises. So that's pretty simple and straightforward. So read 8088. Reading from that address. Okay, so we start off, we go let's set these pin numbers, modes. This will be slightly different now. So 31 to 36 will be output. 37 to 44. 31 to 36. 36 there and 37 there. Okay, so clock starts high always. Actually, what I didn't do in this one, silly me, when does right go low? At the top here, I need to have right as high. And read as high. Then right goes low at the beginning of T2. Here. 8088, right low. And it goes high at the beginning of T4. When that clock goes low, the right goes high. Okay, and then stays high. So we have write and read and clock all start high. Okay, then we have for the read cycle. Clock goes low, address gets set, clock goes high. Let's copy this. This first phase is the same. Clock goes low, address gets set, clock goes high. We then have basically another one for the address. This is the same as we have here. Which is the second part of the address, but we're doing nothing there. Actually, that has the read being set on there, doesn't it? So here, the read is low here. the read signal goes low here, partway through the first bit of T2. And then we're on to T3, where we then do the read. Clock goes low. Nothing happens. Clock goes high. Need a storage variable to put the value into. Then we read all the bits. So I have val is already 0, so val or equals digital read in D0. Question mark 1 0. I'll bracket that just in case. 8 of those. And 8 bits. Okay, so we've done the read at this point here. We then have a delay. That's the end of T3. Clock for release. There's a lot to do here. We go down, we raise our read signal. The address we don't care about, it stays what it was. Data is already input. So it's just raise, delay, raise clock, delay. Delay, raise clock, delay. And return the value, of course. Okay, this won't compile, I know that for a fact. What's that? Pin 8088 clock high hiding in there. That should be a comma. All over the place. Lots copy paste errors there. Okay, oh, that compiled. I'm surprised. I had a feeling that things like pin D0 would conflict with other defines, but maybe not. Right, so let's do a switch in here. Get feet hid. Get feature 1. So this looks at what kind of bus has been selected. 0, which should be the default, is 8088. V equals. And this is right, isn't it? I'm on here. And the same up here. B equals read 8088 to 0. Now I need to send a report. Send report is a buffer and a length. That's easy because it's a single byte report. So the buffer is ampersand v and the length is 1. That might work, or it might not. Who knows? I need to compile. Right, but I've got no way of testing if this is going to do anything yet. I'm just working purely out of my own strange brain. I shall try installing it. There we go, that's loaded. Yep, it's there in the USB list, my bus emulator. Okay, so what I'm going to need now is to work on the Linux side of things, I think. What time are we at? Oh, getting towards 4 o'clock. I'm supposed to be finishing soon. Right, I'm not going back on the Linux side of things just yet then. I shall do that in my next session of doing this. So, what do we have? We have the beginnings of a possible firmware that I don't know if it'll work. It compiles and it installs and it runs, but who knows what it'll do. Next is to make the Linux code to test it. That isn't actually as hard as it would seem. I've done similar code before in the past and it's pretty straightforward. We're doing it all in C, of course. I don't hold with any of this Python nonsense. Yeah, that'll be my next job with this. I've got a clear idea of how I want it to work anyway, so... Right. Tomorrow I won't be... tomorrow is... What day is tomorrow? Thursday. I might be streaming. I'm out working in the morning. Tomorrow afternoon I might get time to do another stream of this. Do some work on the Linux code for this tomorrow afternoon. Should be possible, yes. Yeah, we'll say again 2:30 tomorrow probably. Stream again doing the Linux code side of things and see if I can get this to actually do anything. It would be nice if it would, but who knows. Right, well, I'm going to call it there then. That's enough for today. I shall pack up my streaming kit and all goes well, I shall see you tomorrow. Thank you for joining us today. And if you're watching this on the VOD, then I suggest you follow me on Twitch to catch my next stream so you get alerted if the alerts work. I do find them so hit and miss, Twitch alerts. I'll get an alert that a stream is starting a good half an hour or so into the stream sometimes. So yeah, follow me on Twitch. I'll probably upload this VOD to YouTube, so if you're watching me on YouTube, join me on Twitch live sometime. It's more fun. You get to chat to me then. I've got a Discord channel. Links are in the descriptions / about pages, wherever you happen to find these things. Join me on there to discuss things. Find me on... I no longer use Twitter. I've deleted Twitter since Elon Musk took over and messed it all up. But that's another story. So yeah, you'll find me on Discord modes mostly. Yeah, well, I'll see you tomorrow or whenever you happen to next swing by.